Hello guys, welcome back to my channel. My name is Tony and today we are going to continue our journey to Leetcode and we are going to talk about this word search number 2. And let's go ahead and read the question. And we are given a m times n word of characters and a list of strings words, and we're going to return all the words on the board, and each of the word must be constructed from the letters of sequentially adjacent cells, where the adjacent cells are horizontally or vertically neighboring, and the same letter cell may not be used more than once in the word. So let's go ahead and check one of the example right here. So we are given the board, which is represented on the graph right here, and we also have a words and composed with word and individual word right here, and those are the initial inputs, and the result is gonna be we're gonna find as many word within words, as many as possible within this the board. So how do we do that? And the way we do that, before we do that, right, before we think about the algorithm, so we can check the example right here. So we have oath, and we started with O, and we know A is there, and T is there, and H is there, so we can compose the oath right here. And we also have the eat, and which is right here. So E, start with E, and we going left, and we see A, and we going left again, and we are seeing T, and that composed eat, and then that's gonna be the final result for our list. Unfortunately, we cannot form the P because we don't even have letter P within this board, and we have letter R, but if you check the neighbors, and for R we only have E, we have K, we have V, so from the horizontal or the vertical perspective, we are not going to see any neighbors has the letter A to compose with a ring, so that's why we just simply give up. And now that brings us to the next question. So how do we know that if we should continue search or not? So we need a data structure to tell us that. So if we see a letter, so if this letter is in the words or not, so by simply seeing the words we cannot do that. So why? Actually you can, and doing the brute force search, and within this words list, every time you loop through a character and you check, hey, if this character is in the first letter or the second letter of the words and stuff like that, and that matching is gonna take a lot of time. The time complexity is gonna be doubled in this scenario. So can we do better? Can we do better than brute force? And the answer is yes. So there's a data structure. There are actually like a couple of data structures we can use, and let's check the one of the example right here. So we're just gonna use a oath to we're gonna use oath as an example right here. So, and the first data structure we can use is by using dictionary, which is the hash map, and we're gonna waste some spaces to form a prefix dictionary. So what does that mean? I'm gonna show you guys right here. So we're gonna have OA and OAT and OATH. So at each prefix for the word, and we're gonna store that prefix as a key and the word as the value. And like once we, for example, we are going through here and we are seeing O, and the O is actually a key within the dictionary, and we can keep searching, and then we're tracking down whatever the characters we're seeing. If we're going left and we are seeing OA, and perfect OA is another key within this dictionary, so we can keep searching. And for example, we are going to the right and we are seeing OAA, and we don't see OAA as a key within this dictionary, so we are not gonna search on the right hand side. So we're gonna go down and check. So we have OAT, and perfect OAT is a prefix within dictionary, so that's perfect. So that's how we search by using dictionary. So we're just gonna do this pre-processing for all the words we have, and to store all the prefix within the key for the dictionary, and then we can do the searching by doing the backtracking. That's great, and that's one of the great solution we have. So the only issue is that can we do better? Can we do better? And you know, like we are wasting a lot of the spaces right here. We have O and OA and OAT, and those duplicate words are wasting spaces. So, and the answer is like we do have a better data structure to fit in this need, and which is try. And try is gonna be like a tree, and formed by that character. And try is very good to dealing with the prefix issue. So let me show you guys an example I have in my mind. So I'm not gonna use these 4 words and because they are redundant. And let's try one of the good way to demonstrate the try. So we have apple, app, and let's try another word start with A. Let's call this amen. Okay. Um, so each try will have a root, and we have a root, and the roots in this case, like let's form a apple first. So the next layer is gonna be A because we know that apple start with A, and another layer, and each character is gonna be a try node, and the next layer is gonna be another try node, but it's gonna be connecting with the hash map. So the next layer is gonna be P, and the next layer is gonna be just imagine this is just a regular tree, multiple ternary tree, and we're gonna have APP, and L is gonna be on the left hand side of the P, so we're just going to the left, and E is gonna be the left as well, so we're going to the left, and now we formed apple. So this is the try, how the try looks like, and so since we finished the word, and we're gonna indicate that this is a word, so we're gonna use a boolean value to indicating that hey, we already reached the word, and we just mark this up as a word. uh the next word we're gonna mark is gonna be apple. Oh, app. So we know app is right here, we already have that, so we don't have to create another try node to indicating this is P or P because we already have the apple right here, and all we need to know is app is a word. So all we need to do is indicating that hey, this is a word. So we're just gonna indicating this right here. And then we have the third word, which is the amen. Okay, so M is on the left hand side of the P, and then we're just going left, and E, and then and something like that. And then so this is the third word, so like and, so we're also gonna indicating this is the word, so I'm just gonna use a dash to indicating that. Okay, now we are done. This is gonna be the data structure for try, and that's all the spaces we need. So each node is gonna be, each character is gonna be a node, and the node will just have the one character, and then once we're going into the next layer, we're gonna have M and P. So when you're going through, for example, within this word, and if you are searching these 3 words, and if you are seeing A, you know that hey, you are in the first layer, so perfect, you can keep going forward. If you are seeing M and P in the next layer, for example on the horizontal neighbor or the vertical neighbor, and you are seeing M and P, so you can continue, otherwise you are not going to continue. And that's the try data structure just facilitate how you searching the final results like that. And since we know that, we're going to use try as the data structure. And what are the other things we need to know? And I think I already mentioned that. So just to remind you guys again, this is a searching problem. We're gonna use backtracking to find all the possibility solutions we have. So we're gonna start with every single position. So we're gonna start right here, and we're gonna start right here, and we're also gonna start right here. We're gonna loop through the entire board and start from anywhere and searching for all the possible and words we can formed by this board. And remember, there's another caveat is that we cannot use a cell more than once. So it's not you might be confused like, hey, we have the oath right here, we have the T right here, it right here, and we already duplicated the T. And so what the question is asking is, you cannot use a word twice. For example, that you have a T A, and you cannot go back to the A and you reuse the A in the same word, and we cannot use the the same letter cell more than once in one word. So but we can like have the duplicates intersection right here. So no, that's gonna be fine. Okay, now we have all the toolbox to solve this problem. So we are gonna just continue to write it, and let's go ahead to write it. Um, Let me just make a little bit more spaces before that. So we need to make another class called the try, and the try is formed by try node. So before that, so we need to do a try node. And so what's try node? Try node is formed by character, and we have two things within this try node. And the first thing is gonna be, let me just write it down first. So we have to build a constructor, and so what's within the try node? And every single time we're gonna have a character within this try. and this character is indicating by the key. So we're gonna use a hash map to storing that. So we're gonna use a children. So let's call this guy. You know what? Let's just do something like this. So we're gonna use a hash map to storing whatever we have in the next layer. And for example, in this layer, we have the empty try node, and the next layer we're gonna have a. So we are gonna use we're gonna build another try node just by using that. And another thing we have to know is for each node, and is that a word? Can that form a word or not? And that's gonna be a boolean, and we're gonna use a boolean to indicating if we already have the word or not, and the default is going to be false every time that when we inserting the word. And if this is a word, so we flip the boolean value and we turn this to the true. And now we have the try node, and we're gonna form a try. So how do we form a try? And let's go ahead and write it. We also need the constructor, and within the constructor we need a root. The root is gonna be empty, so let's just define a empty try node. And we have the empty try node, and like within this problem, in the future we're gonna cover a little bit more for try, but within this particular problem, the only thing we need is the insert function, because we're gonna insert all the words within word, all the word within words into the try. So all we need to do is to insert, and then we want to check if the try has the word in the try data structure or not. And every time we do the traversal, and we're gonna start with the root, and which is the empty root right here. And every single time we are seeing a character within this word, you know what? Let's do one of the example. Let's say apple, and we're gonna split the apple into 5 different components, A, P, P, L, E, and we know A is gonna be the next node, and something like that. And we're gonna do something like this. For each character within this word, and we decompose the entire word into different characters, and then we are checking if the characters is in this node. Okay, node children. Is that right? Okay, so if the character is not in the children, and then we create one, so the node children character will be equal to try node, and we create a empty try node, and in the future we're gonna modify this try node. And if we have like more components, and we're gonna modify on top of this try node, and then we are gonna be continue, and the node will be equal to the node and try children for this character. Okay, and once we finish that, and we indicating that this particular node is gonna be a try node. So let's just go through this piece of code, and before we get more confused. So we are starting with the empty node right here, and then we're gonna check, hey, if A is in this try node, the children property, and most likely it's not, because we have a empty root, and then we're gonna insert that. So the way we insert that is by assigning the node, which is the root, and the node is gonna be root right now. The root next layer will be assigned with A. So now we assign it with A, and a empty try node. So we already have A corresponding. So the key is gonna be A. The key is gonna be A, and the value is gonna be an empty try node. Now we have this part, and once we have this part, and then the node will continue to scroll down, and node is just a pointer. So initially we are pointing at the root, and then now we'll keep going down, and we're going all the way to A, and A is gonna be the next layer, and then we keep inserting. So what are we gonna insert? We're gonna insert a P. So when we come up to P, for example, that word is apple, right? The second character is gonna be P, and once P comes in, and we are checking, hey, is P in the A's try node right now? It's empty. It doesn't have anything. And Is P in it? No, of course not, because we have an empty try node. And the way we're gonna do that is by assigned try node A another value. So we have the key is gonna be P, and corresponding to the try node, and it's gonna be an empty try node. All right, so A has next layer now, which is P, and we just keep going until we see the last one, E, and we assign this. Like the node is a pointer, so node initially is in root, and once we assign A, and it's gonna come to A, and come to P, come to P, come to L, come to E. Once it come to E, we're gonna assign this node is word as true, and we know this is true. And every single node will have the isWord property attribute, and the default is going to be false, but only once we finish the inserting and we assign this guy as a true, and that's how we do the inserting. Okay, so that's how we do the try. I think I explained. I think that's a good explanation for the try, at least for the basics. Now we already have the toolbox, so we know the try, and all we need to do for the rest of the story is going to be implementing the backtracking part. And before we do the backtracking part, just like all the BFS, we need to define the boundaries, and that's going to be M and N, and we also need a result, which is the list, and we also need a try, and the try is going to be defined as try, and which is what we defined right here. So by the time we define a try, we already have the empty sub root and being assigned, and which is the try node, and that's gonna be the empty try right here. And all we need to do is we're gonna you know what, so for word in words, and we're gonna insert all the word into the try. And so for example, like we have apple, app, ammon, and those words will be inserted into the try, and then we can start doing the searching. And the way we do the searching is by looping through each of the characters within this board, and we already have the M and N, so we just continue to searching. And then so every time we loop through one of the initial positions, so we need to start doing this. And so what do we need to pass in? So every time, so we are looping through to the each character within this board, and hopefully like start from anywhere, so we can search for a word, and we can start with O, A, and stuff like that, etc. And the things we're gonna pass in for the recursive function is gonna be the board. At least we're gonna have the board, and also the position for the word. And the reason we pass in the position is that the character is that we need a position, we need the coordinates. And because we're going to search for the left and right, up and down, we're going to search for all the neighbors. So we need coordinates. And we don't need the character right here because we can just get the character by using the board with the corresponding coordinates. And then once we have that, and what else we need? So we need a path to track what we already have. For example, we start with O. If we're going to the right and we have OA, and we have to track all the prefix as a path, and to checking, and then we check if that's in the try or not, right? So that's the path we need. Also the result. We need the result to check. Okay, I think that's everything we need, and also we need to try, right? We need to try. Do we need to pass? How do we pass the try? You know what? So since we need a pointer, every single time that we start with the try, just like the linked list, we start with the head, and if we have try as the pointer, like once we traverse to the bottom, we cannot go back. So the way we normally do that is by create a dummy, just like linked list. We normally create a dummy, and within try, so we also need a dummy like this. So the try root is gonna be the node, and I think all we need to do is pass in this node. All right, and then the rest of the story is just implementing the DFS, which is the backtracking. I'm naming this as DFS, but then essentially it's gonna be a backtracking function. and we are gonna have the board, and we're gonna have board, and we're also gonna have the node, and we're gonna have I and j and path and result. Um, once we have that, think about what we need to do the next, and we need to check if we have this. So we need to get the character out. So I and j, and once we're getting this guy out, and we're gonna check if this is being included within this try data structure. So as we know that try is gonna be the node, and all we need to do is check if we have this guy. So node uh dot children can read tab today. So we got this guy. And we are checking if this character is within this try, just like we are checking the hash map. So, and then we can assign this guy as node, and we can rename him. And we are checking if the node is there, that's perfect. If not, we just return nothing. So we're just gonna return the empty results. So in this case, we are not gonna find anything. Just for example, k, right? Like the try to the next layer, we only have P, we have E, we have R, we have O, but we don't have anything else. And so if you start with K, so we are not gonna even further doing the search. Once we finish that, if we are not returning the empty result, that means like we have a character within this try, so we can continue searching. So we can go ahead and go to the next layer. So the way we go to the next layer, we are gonna store this particular character, and that's how we doing the backtracking. And the way we do backtracking is by assign this guy to something strange character, and then we can. That's for dealing with each cell cannot be reused. So for example, that like we mentioned in the example, if we start with A, T, and we cannot reuse this A. So every single time you traverse to somewhere, you wanna convert this particular character into something like a strange character that we never gonna use. And once we finish using that, and then you convert it back. But once you convert it back, like you don't know what that is, right? So that's why we need to store that particular characters into the temp variable. So that's more like a standard backtracking. And then we're gonna exploring all the neighbors we have. So the rest of the story is just gonna be standard. So -1, 0, and 1, 0, and we are going for all the 4 directions. Perfect. So, and then we're gonna name it as x plus I j plus dy, and we're gonna exploring all the 4 directions, and we're just calling the recursive function, and we passing the board, which does not change, and node. Wait, so I think node should changed. Let's come back and see. Okay. And then we're gonna have x, and then we're gonna have y, and we're gonna have the path, and plus 10, and we're gonna have result. Okay, so I think the framework should be like this, and we also need the base case. But before we go into the base case, let me just confirm that the node will be equal to the next layer. So the node is already being shifted. So at first we are checking A, apple, for example, apple. We are checking A, and next layer we're gonna check P. So in this case, the node is already going to the children, so that's perfect. And then so once the case is that we're gonna see a word, and it's the case that the node is already is word, right? So all we need to check is if node is word, that means like we are checking if the is word is true. So if it's true, and we can just append the current path, which is the prefix that we are currently tracking, and we know this prefix already formed a word, and then because we don't want to record a word twice, and then we record this guy as false and temporarily. All right. And we know that this word, we don't want to duplicate the word, right? So for example, we already know that EAT already being formed. And for example, there's another EAT, we just don't want to do that. And we're just tracking this guy as false in the try. So we just don't want to have the repetitive result. And once we have that, and I think we should be good. And this is one more thing. And since we are given the coordinates, and normally we have to check that if we are within this word or not. And that's going to be simple. We are checking if the I is less than 0 or J less than 0 or I is greater or equal to M. We also need to have the M and the N being defined right here. Or J greater or equal to N. And if that's the case, we're also going to return. And let's try if this works or not. Okay, it works. So I just did it like an hour ago. Okay, so I think this is a good explanation. So let me know if you guys like. You know what? Let's do a quick recap. So the way we do that is by storing all the word within this words into a data structure. So we can either use a hash map or we can either use a try. The try is going to be a prefix tree. So it's going to tell us that if we can continue doing the search or not. And so once we have the data structure tries being ready and we have the prefix tree, and then we can do in the backtracking. And the way we do backtracking is we start with any characters and we do recursive function to finding the neighbors if we can keep searching or not. And the way we can keep track that if we can keep searching or not is like this line. And this line will tell us that we have matched the prefix or not. And if we are matching the prefix, and we're gonna search for the next character. And how do we find the next character? We are looking for all the neighbors horizontally or vertically. And we keep searching for the 4 directions and doing the backtracking. And the way we do backtracking is that we also don't wanna use the same cell multiple times. And the way we keep avoid that is by replacing the current character to different strange character, and then we revert it back right here. So we use the path to track the prefix that we already tracked, and if we the try tell us that it's a word, and then we just put that into the path into the result, and then we just return that. And in order to keep away from the duplication in the final result, and we turn the flip off by reverting that to false. All right, so let me know if you guys have any questions. I'll stop the video right here.